In October 2022, the James Webb Space Telescope detected something that should not exist. A galaxy. Fully formed. With hundreds of billions of stars already burning bright. Located so far away that we're seeing it as it appeared just 300 million years after the Big Bang. This shouldn't be possible. According to everything we understand about physics, about time, about the formation of structure in the universe, there simply wasn't enough time for this object to exist. But there it is. Massive. Ancient. Impossible. And it's not alone. Across the observable universe, in the deepest images ever captured, astronomers are finding objects that violate the fundamental timeline of cosmic evolution. Galaxies that assembled too quickly. Stars that ignited too soon. Structures that organized themselves in the cosmic blink of an eye. Each discovery chips away at our understanding of reality itself. What if the Big Bang timeline is wrong? What if the universe is older than we calculated? What if something else, something we don't understand, accelerated the formation of everything we see? Today, we journey through evidence that challenges the very foundation of modern cosmology. We'll examine discoveries that have left the world's leading astrophysicists questioning decades of established science. We'll explore what these impossible objects reveal about the nature of time, space, and cosmic evolution. Prepare yourselves. We begin. July 2022. The James Webb Space Telescope completes its calibration phase and begins scanning the deepest reaches of space. Its primary mirror, 18 hexagonal segments of gold-coated beryllium spanning 6.5 meters across, collects light that has traveled for over 13 billion years. The telescope turns its gaze toward a patch of sky no larger than a grain of sand held at arm's length. Deep field observations, astronomers call them. Windows into the universe's earliest moments. What JWST found would trigger an immediate crisis in cosmology. Among the countless points of light in that first deep field image, one galaxy stood out. Not because it was beautiful or unusual in shape, but because of where and when it existed. The galaxy, catalogued as Glass Z13, emitted light from an era just 300 million years after the Big Bang. But it wasn't a small, primitive collection of stars struggling into existence. It was massive. Fully assembled. Already containing stellar populations that should have required billions of years to form. Think about that timeline for a moment. 300 million years sounds like an eternity. But in cosmic terms, it's nothing. A blink. The universe at that age was still in its infancy, a hot, dark place where the first stars had only just begun to ignite. 3:30 to 5 o'clock. The Standard Model's timeline according to the Lambda Cold Dark Matter model, our best theoretical framework for understanding cosmic evolution. Here's what should have happened in those first few hundred million years. First, there was light. The Big Bang itself. Then came the cosmic dark ages, hundreds of millions of years where the universe contained only hydrogen, helium, and invisible dark matter. No stars. No light. Just an expanding void of gas cooling in the darkness. Eventually, gravity began its patient work. Dark matter clumped together first, creating gravitational wells. Normal matter fell into these wells. The first stars ignited massive, primitive objects made purely of hydrogen and helium. These population 3 stars, as astronomers call them, lived fast and died young, exploding as supernovae and scattering the first heavy elements into space. Only then, after this first generation of stars lived and died, could the second generation begin to form. And only after several such generations could you build something as complex as a galaxy with hundreds of billions of stars. This process, according to every simulation we've run, should take at least 500 to 700 million years. Maybe longer. Glass Z13 existed at 300 million years. 5 to 7 o'clock. The problem deepens. Dr. Evo Lab at the Swinburne University of Technology was among the first to analyze the spectroscopic data from Glass Z13. What he found disturbed him. The galaxy wasn't just present too early. It was too evolved. The light spectrum revealed stars of different ages and compositions. Multiple generations of stellar populations, already chemically enriched with elements heavier than hydrogen and helium. This suggested a formation history extending back even earlier, perhaps to just 200 million years after the Big Bang. We're seeing galaxies that shouldn't exist according to our current models, Lab stated in a paper that sent shockwaves through the astronomical community. It's as if we found a fully grown oak tree in a forest that was planted yesterday. But Glass Z13 represented just one data point. Perhaps it was an outlier. An exception to the rule. A statistical anomaly in a universe governed by probability. Then JWST found another. Within 6 months of JWST's operational deployment, astronomers had identified over 24 galaxies that violated the standard formation timeline. Each one massive. Each one ancient. Each one impossible. Soars 93316. A spiral galaxy with organized structure appearing just 250 million years after the Big Bang. Spiral galaxies require time to develop their characteristic arms through gravitational interactions and stellar feedback. Yet here one was, fully formed, in an era when the universe was supposedly still dark and chaotic. Jade's GSZ 13-0. Another massive galaxy at 330 million years, but this one showed evidence of a supermassive black hole at its center, an object containing millions of solar masses. Black holes of this size should take billions of years to form through the accumulation of matter. How did one grow so enormous so quickly? Jade's GSZ 14-0. The current record holder for the most distant galaxy ever observed, existing just 290 million years after the Big Bang. Not only is it impossibly early, but it's producing stars at a rate that exceeds the theoretical maximum efficiency of gas-to-star conversion. Each discovery added to a mounting pile of evidence that something fundamental in our understanding was wrong. Dr. Mike Boylan-Colchin at the University of Texas at Austin ran the numbers. Using the standard cosmological model, he calculated the probability of finding even a single galaxy as massive as Glass Z13 at such early times. The odds were roughly 1 in a million. Finding 24 of them? Astronomically improbable. Literally. Either we're living in an incredibly unlikely universe, Boylan-Colchin wrote, or our fundamental model of cosmology needs serious revision. Other astronomers pushed back. Perhaps JWST's measurements were wrong. Perhaps the redshift calculations, the method we use to determine cosmic distances, contains systematic errors. But as more data accumulated, the measurements held firm. Independent analysis confirmed the distances. The impossible galaxies were real. The crisis deepened. Here's why this matters beyond academic debates about galaxy formation timelines. The lambda cold dark matter model isn't just some random hypothesis. It's the culmination of nearly a century of observation and theoretical physics. It successfully predicts the cosmic microwave background radiation. It explains the large-scale structure of the universe. It accounts for how galaxies cluster and how the universe expands. It is, quite literally, the foundation upon which modern cosmology rests. And now, the most powerful telescope ever built is finding objects that contradict it. If these early massive galaxies are real, and every piece of evidence suggests they are, then one of several possibilities must be true. The universe is older than we thought. Dark matter behaves differently than we assumed. The laws of physics operated differently in the early universe. Or something else, something we haven't even conceived of, was at work in those first few 100 million years. Standing in the observation control room at the Space Telescope Science Institute in Baltimore, astronomers face a choice. They can dismiss these findings as anomalies, statistical flukes that will resolve with more data. They can adjust parameters within the existing model, tweaking the physics to accommodate the observations. Or they can confront an uncomfortable possibility. That we've been wrong about something fundamental. As Dr. Dan Coe, one of the lead astronomers analyzing JWST's deep field data, put it. We're either seeing the universe do something we didn't think was possible, or we're discovering that our entire timeline needs to be rewritten. But the evidence forces us to confront an uncomfortable possibility that the impossible galaxies are merely symptoms of a much deeper problem with our understanding of cosmic time itself. The galaxy problem extends beyond just stars assembling too quickly. At the centers of many impossible galaxies, JWST discovered something even more troubling: supermassive black holes that shouldn't exist. In January 2024, astronomers using JWST identified a quasar, an actively feeding supermassive black hole designated J0148+0600. The light from this object traveled for 13.03 billion years before reaching us. We're seeing it as it appeared when the universe was only 700 million years old. The black hole at its center contains 1.6 billion solar masses. To put that in perspective, our Sun would need to consume the equivalent mass of another star every single day for 1.6 billion years to reach that size. This black hole managed it in just 700 million years, during a period when matter was spread thin across space and should have been difficult to accumulate rapidly. But J0148+0600 wasn't an outlier either. Scientists discovered a black hole containing 40 million solar masses at a distance corresponding to just 470 million years after the Big Bang. The research team from the Center for Astrophysics, Harvard and Smithsonian found it embedded in a galaxy that was itself far too massive for its age. Then came the discovery of SURS 1019, hosting a black hole with 9 million solar masses at 570 million years after the Big Bang. Analysis of its light spectrum revealed the black hole was actively consuming matter, growing larger by the day. In March 2024, a team using both JWST and the Chandra X-ray Observatory identified a black hole with an estimated mass exceeding 100 million solar masses at redshift z equals 10.3, approximately 480 million years after the Big Bang. 100 million solar masses in less than half a billion years. Current astrophysical models suggest black holes grow through two primary methods: by consuming gas and stars from their surroundings, or by merging with other black holes. Both processes have efficiency limits. A black hole can only consume matter so quickly before the energy released from infalling material actually pushes new material away. This is called the Eddington limit. Even assuming continuous feeding at the maximum possible rate, starting from a seed black hole created by the first generation of stars, the models predict maximum black hole masses of perhaps 10 to 20 million solar masses at these early times. Not 100 million. Not 1.6 billion. Dr. Priyangvada Natarajan at Yale University, a leading expert on black hole formation, outlined the problem in stark terms. "We're facing what I call the seed problem," she explained. For these supermassive black holes to exist so early, they need to start from much larger seeds than our models allow. The traditional scenario suggests the first black holes formed when the earliest generation of massive stars, perhaps 100 to 300 solar masses, collapsed at the end of their brief lives. This would create stellar mass black holes of perhaps 10 to 50 solar masses. But you can't get from 50 solar masses to 100 million solar masses in 500 million years, even with perfect efficiency. Some astrophysicists proposed that perhaps black holes could form directly from collapsing gas clouds, bypassing the stellar stage entirely. These direct collapse black holes might start with masses of 10,000 to 100,000 solar masses. Better. But still not enough. The black holes JWST is finding require either seed masses far larger than any proposed mechanism can produce, or growth rates that violate the laws of physics as we understand them. Or they require more time than the standard cosmological model allows. The evidence extends beyond just the presence and mass of early galaxies. It's also about what they're made of. When astronomers analyze the light from distant galaxies, they can determine the chemical composition of their stars through spectroscopy. Different elements absorb light at specific wavelengths, creating a unique fingerprint. The first stars in the universe, the population 3 stars, should contain only hydrogen and helium, the elements created in the Big Bang itself. Every heavier element, what astronomers call metals, had to be forged in the cores of stars and then scattered into space through supernova explosions. Building up significant metallicity takes time. Generations of stars must live and die, each one enriching the interstellar medium with heavier elements. Yet when astronomers analyzed the spectra of galaxies at redshift z equals 10 to z equals 13, 300 to 400 million years after the Big Bang, they found stars with surprisingly high metallicity. Not population 3 stars at all, but population 2 or even population I stars, stellar populations enriched with carbon, oxygen, iron, and other heavy elements. This implies that multiple generations of stars had already lived and died. The necessary stellar life cycle had already played out completely. In just 300 million years. Perhaps most remarkably, many of these early galaxies display structure, organized patterns that shouldn't emerge so quickly. Source 93316, the spiral galaxy at 250 million years, shows clear spiral arms. These features require specific conditions. A rotating disk of stars, differential rotation that shears the disk into spiral patterns, and sufficient time for gravitational interactions to organize the structure. Computer simulations of galaxy formation consistently show that spiral structures don't appear until at least 1 to 2 billion years after a galaxy begins assembling. Yet here one stands, fully formed, in a quarter of that time. Other early galaxies show evidence of stellar bars, elongated structures of stars stretching across their centers. Bars form through complex gravitational resonances that require time to develop. Some early galaxies even show evidence of multiple stellar populations with different kinematics, suggesting mergers had already occurred. All of this structure, all of this organization, all of this evolution, in what should have been the universe's first morning. But this represents just one piece of a much larger puzzle hidden in the cosmic microwave background itself. While JWST was discovering impossible galaxies, another crisis in cosmology was reaching a breaking point. For over a decade, astronomers had been measuring the expansion rate of the universe using two independent methods. And the methods gave different answers. The Hubble constant, the number that describes how fast the universe is expanding, could be measured by looking at the cosmic microwave background radiation, the afterglow of the Big Bang. Using data from the Planck satellite, this method gave a value of approximately 67 kilometers per second per megaparsec. But when astronomers measured the Hubble constant by observing nearby supernovae and other stellar distance markers, they got a different number. Approximately 73 kilometers per second per megaparsec. 6 kilometers per second per megaparsec might not sound like much. But it's a 9% discrepancy. And the measurements on both sides were precise enough that random error couldn't explain it. Something was wrong. Either our understanding of the early universe was incorrect, or our understanding of cosmic expansion was flawed, or both. In 2023, a team led by Dr. Wendy Friedman at the University of Chicago made a startling connection. If the impossible galaxies were real, if structure really did form faster than the standard model predicted, then perhaps the universe was expanding differently than we thought in those early epochs. A faster early expansion rate would provide more time for gravity to work. It would allow dark matter to clump more efficiently. It would give those first stars and black holes the extra hundreds of millions of years they needed to grow large. But a faster early expansion rate would also affect the cosmic microwave background in subtle ways. Ways that might explain the Hubble tension. The impossible galaxies weren't just a problem for galaxy formation theory. They might be a symptom of something fundamentally wrong with our model of cosmic expansion itself. The evidence takes another strange turn when we examine how matter is distributed in these early galaxies. Dark matter, the invisible substance that makes up 85% of all matter in the universe, is supposed to behave in predictable ways. It should form large halos around galaxies, with matter concentrated toward the center and tapering off toward the edges. But when astronomers used gravitational lensing to map the dark matter distribution in early galaxies, they found anomalies. Some early galaxies appeared to have less dark matter than expected. Others had dark matter distributions that looked too smooth, too uniform, lacking the clumpy substructure that simulations predict. Dr. Peter van Dokkum at Yale University, analyzing lensing data from both JWST and Hubble, noted. The dark matter in these early galaxies doesn't behave like dark matter in nearby galaxies. Either it's distributed differently for some reason, or our understanding of how dark matter behaves in the early universe needs revision. One theoretical explanation gaining traction is that dark matter might interact with itself more strongly in the early, denser universe. These self-interacting dark matter models could explain the smoother distributions. But they would require modifying our fundamental understanding of dark matter's properties. Another piece of the standard model crumbling under observational pressure. Zoom out from individual galaxies to the large-scale structure of the universe, and the problems compound. The cosmic web, the vast network of filaments and voids that organizes galaxies into a phone-like structure, is one of the universe's most distinctive features. Dark matter forms the scaffolding, with normal matter tracing the densest filaments. This structure should take time to develop. Billions of years for gravity to organize matter on such vast scales. In August 2024, astronomers using JWST's Whitefield instrument discovered a massive cosmic filament at redshift z equals 8.7, corresponding to roughly 600 million years after the Big Bang. The filament stretched across 13 million light-years and connected multiple early galaxies. Computer simulations consistently predict that such large-scale structures shouldn't emerge until at least 1 to 1.5 billion years after the Big Bang. Yet here was one, fully formed, at 600 million years. Further observations revealed additional filaments and even protoclusters, regions where dozens of galaxies were already congregating in dense groups. The cosmic web, it seemed, had organized itself far faster than physics should allow. Perhaps the most remarkable discovery involves what astronomers call quenched galaxies, galaxies that have stopped forming new stars. When a galaxy runs out of cold gas, or when feedback from supernovae or black holes blows the gas away, star formation ceases. The galaxy's light shifts toward redder wavelengths as its massive blue stars die off, leaving only longer-lived red stars behind. This quenching process typically occurs in large galaxies that are billions of years old. The mechanisms that shut off star formation require time to operate. In December 2023, a team analyzing JWST data identified a quenched galaxy at redshift z equals 7.3, about 700 million years after the Big Bang. The galaxy showed no signs of active star formation. Its stellar population appeared old and red. "We're seeing a galaxy that's already lived its entire life," said Dr. Tobias Lusser from the Kavli Institute at Cambridge. It formed, made its stars, and died all before the universe was even a billion years old. It's like finding an elderly person in a world where everyone should be a newborn. The evidence extends beyond black holes and galaxies into the realm of cosmic time itself. What we're witnessing might not be impossible objects at all, but rather evidence that the universe is fundamentally older than we've calculated. The lambda-cold dark matter model, refined over decades of observation, rests on several pillars. The universe began 13.8 billion years ago in the Big Bang. It contains approximately 5% normal matter, 27% dark matter, and 68% dark energy. The cosmic microwave background provides a snapshot of the universe at 380,000 years old. Structure formed hierarchically, small objects first, then larger structures assembled through mergers. This model successfully predicted countless observations. It explained why the universe is flat. It matched the temperature fluctuations in the cosmic microwave background. It reproduced the distribution of galaxies across space. Until JWST looked deep enough to test its predictions about the earliest epochs. Now, faced with impossible galaxies, supermassive black holes that grew too quickly, and structure forming too rapidly, cosmologists are being forced to reconsider fundamental assumptions. "We're in a situation similar to the early 20th century," explained Dr. Adam Rees, Nobel laureate and astronomer at Johns Hopkins University. "We have a successful theory that explains most observations but fails spectacularly to explain others. That's usually a sign that we're on the verge of a major breakthrough or a major revolution in our understanding. Some physicists suggest the problem lies not with the timeline but with our understanding of gravity itself. Modified Newtonian dynamics, (MOND), and related theories propose that gravity behaves differently on cosmic scales than Einstein's general relativity predicts. Under these frameworks, structure could assemble faster because gravity's effectiveness increases in low acceleration environments like the early universe. Dr. Stacy McGaw at Case Western Reserve University has long advocated for such alternatives. The rapid formation of structure we're seeing might indicate that gravity is more efficient at organizing matter than we thought, he suggested. If gravity operates differently in the early universe, many of these impossible observations become expected outcomes. However, modified gravity theories face their own challenges. They struggle to explain the cosmic microwave background in gravitational lensing observations that general relativity handles elegantly. Most cosmologists remain skeptical that modified gravity can resolve the impossible galaxy problem without creating new contradictions. A more conservative solution gaining traction involves early dark energy, a hypothetical component of the universe that existed only in the first few 100 million years after the Big Bang. Standard dark energy, the mysterious force causing the universe's expansion to accelerate, appears constant over time. But early dark energy models propose that an additional energy component existed briefly in the young universe, contributing perhaps 10 to 15% of the total energy density before decaying away. This extra energy would have affected the expansion rate, allowing more time for structure formation in those crucial early epochs. It could explain both the impossible galaxies and the Hubble tension simultaneously. Dr. Mark Kamiankowski at Johns Hopkins University, one of the leading proponents of early dark energy, outlined the appeal. Early dark energy provides a minimal modification to the standard model. We're not throwing out decades of successful cosmology. We're adding one new ingredient that addresses multiple observational puzzles at once. In 2024, several research groups published papers showing that early dark energy models could reproduce JWST's observations of early massive galaxies while maintaining consistency with other cosmological measurements. But the theory requires fine-tuning specific parameters to match the data, a feature that makes some physicists uncomfortable. Nature rarely arranges itself so conveniently. A more radical explanation suggests that the supermassive black holes JWST discovered didn't form from stars at all. What if they were primordial black holes, objects created in the first second after the Big Bang from density fluctuations in the fabric of spacetime itself? In this scenario, black holes with masses of thousands or even millions of solar masses could have formed immediately after the Big Bang, providing the massive seeds needed to grow into the billion solar mass monsters we observe. This hypothesis solves the seed problem elegantly. But it creates new questions. What mechanism could create such large density fluctuations in the first place? And why don't we see evidence of these primordial black holes in other contexts? The theory remains speculative, though some researchers at institutes including MIT and Princeton are actively exploring its implications. The James Webb Space Telescope has only begun its mission. As it continues observing the early universe, astronomers expect more surprises. Scheduled observations include ultra-deep fields pushing even farther back in time, to 200 million years after the Big Bang or earlier. If massive galaxies appear there, the cosmological crisis will intensify. Spectroscopic surveys of hundreds of early galaxies, providing detailed chemical composition and stellar population data. This will reveal whether the metallicity puzzle extends across all early galaxies or only specific types. Extended observation campaigns tracking early galaxies over multiple epochs, measuring how quickly they evolve and whether they follow predicted growth patterns. Joint observations with other observatories, combining JWST's infrared capabilities with Hubble's optical observations, Chandra's X-ray detection, and ground-based radio telescopes to build comprehensive pictures of early cosmic structure. Dr. Sandro Takela at the University of Cambridge, co-leader of several JWST early galaxy surveys, anticipates, "We've only scratched the surface. Every deep observation finds something surprising. I expect within 5 years we'll have rewritten significant portions of galaxy formation theory." JWST won't work alone for long. A new generation of telescopes coming online in the next decade will push observational boundaries even further. The extremely large telescope, ELT, in Chile, with its 39-meter primary mirror, will provide unprecedented resolution for studying early galaxies. Its light collecting power will enable spectroscopy of individual star-forming regions in galaxies at redshift Z equals 10 and beyond. The Nancy Grace Roman Space Telescope, launching in 2027, will survey vast areas of sky simultaneously, potentially finding thousands of early galaxies for detailed study. Its wide field of view complements JWST's deep but narrow observations. The Square Kilometre Array, SKA, an international radio telescope project, will map the distribution of neutral hydrogen across cosmic time, revealing when and how the first stars ionized the universe, a critical test of early structure formation models. Together, these observatories will either confirm the impossible galaxies are real and common, or reveal their exceptions explained by unusual circumstances. Either outcome rewrites textbooks. If observational evidence continues mounting that structure formed faster than current models allow, cosmologists will face a momentous decision. Acknowledge the universe might be older than calculated. The current age, 13.8 billion years, comes from combining cosmic microwave background measurements with observations of how the universe expanded over time. Both inputs depend on assumptions about dark energy, dark matter, and the physics of the early universe. If any of those assumptions are wrong, the age calculation changes. Some alternative models suggest the universe could be 15, 16, even 20 billion years old. The extra billions of years would comfortably accommodate the early massive galaxies and supermassive black holes. But accepting a significantly older universe requires explaining why the cosmic microwave background looks the way it does. The CMB's properties tightly constrain the universe's age and expansion history. Changing the age significantly requires changing other fundamental parameters in ways that might contradict other observations. It's a delicate balancing act. Adjusting one parameter to fix the galaxy formation problem might break something else. The impossible galaxy crisis is forcing physicists to reconsider the nature of dark matter and dark energy, the two mysterious components that dominate the universe's mass and energy budget. Dark matter might not be as cold as assumed. Perhaps it's warm dark matter, consisting of particles moving at relativistic speeds in the early universe. This would affect how quickly structure assembled. Or dark matter might interact with itself through previously unknown forces, changing its clustering properties in the dense early universe. Dark energy, meanwhile, might vary over cosmic time rather than remaining constant. Early dark energy models are just one possibility. Other theories propose dark energy was stronger in the past, or behaved differently before the universe cooled. Dr. Licia Verde at the Catalan Institute of Space Studies noted, "We've always known dark matter and dark energy were placeholders for things we don't understand. The impossible galaxies are telling us we understand them even less than we thought." Recent breakthroughs suggest a convergence between the impossible galaxy problem, a Hubble tension, and other cosmological anomalies. They might all be symptoms of the same underlying issue, a fundamental misconception about how the universe evolved. The impossibly fast formation of cosmic structure has reignited interest in a controversial idea: that we might be living in a simulation. Consider the evidence from a different angle. Computer simulations of galaxy formation, the very models that predict galaxies shouldn't exist so early, have limited resolution. They can't simulate every single particle. Instead, they use approximations, starting with dark matter halos of certain minimum masses and building from there. What if the universe operates similarly? What if, rather than building structure particle by particle from the bottom up, the universe was initialized with certain large-scale structures already in place? Dr. Avi Loeb at Harvard, known for his willingness to explore unconventional ideas, suggested, "If we're living in a simulation, the programmer might have started the simulation with certain structures already present to save computational resources. The impossible galaxies might be initial conditions rather than evolved structures." This remains highly speculative. But it illustrates how profoundly these observations are causing scientists to question basic assumptions about reality. Another framework for understanding impossible galaxies invokes the multiverse, the idea that our universe is just one of countless others, each with different physical laws and initial conditions. In multiverse models based on eternal inflation, different regions of space inflated at different rates, creating bubble universes with varying properties. What if our bubble universe has properties that allow faster structure formation than we've assumed? Perhaps the parameters we've measured from the cosmic microwave background don't reflect our universe's true age but rather the age since our particular bubble formed. Other regions of the multiverse might have different ages, different expansion histories, different timelines for structure formation. This interpretation is difficult to test directly, but it provides a framework for understanding why our universe might have properties that seem fine-tuned for rapid structure formation. The most profound implications emerge when we consider the anthropic principle, the idea that the universe must have properties compatible with the emergence of intelligent observers. If galaxies couldn't form in the early universe, if structure assembly required many billions of years beyond what we observe, then the timeline for life's emergence would shift dramatically. The first potentially habitable planets would appear much later. Intelligence would arise much later. Perhaps we're discovering that the universe is optimized for rapid complexity, that the laws of physics and initial conditions were such that structure, stars, planets, and eventually life could emerge as quickly as possible. The impossible galaxies might be telling us something beautiful, suggested Dr. Katie Mack, cosmologist at the Perimeter Institute. That the universe is fundamentally biased toward creating complexity, structure, and ultimately life. That we're not living in a maximally simple universe but in one where interesting things happen quickly. This perspective doesn't solve the technical problems with the cosmological model, but it reframes them. Perhaps rapid structure formation isn't a bug in the cosmic code, it's a feature. Despite all the evidence and theorizing, profound mysteries remain. We don't know what dark matter actually is. After decades of searches, we haven't directly detected the particles comprising 85% of the universe's matter. The impossible galaxies are revealing that it behaves strangely in the early universe, but we still don't know why. We don't know what caused the Big Bang or what, if anything, came before it. The timeline problem with early galaxies might be revealing that our conception of the beginning is incorrect. We don't know if the laws of physics were always constant or if they evolved as the universe cooled and expanded. Evidence for rapid early structure formation might indicate different physics operating in extreme conditions. We don't know if time itself is fundamental or emergent. Quantum gravity theories suggest time might arise from something more basic. Perhaps the impossible timeline is impossible only because we misunderstand time's nature. We don't know if our universe is all that exists or just one region in a vast multiverse. The answer dramatically changes how we interpret the impossible galaxies. And we don't know if intelligent life is common or rare. If structure forms faster than we thought, habitable planets might be older and more abundant. The Fermi paradox, the puzzle of why we haven't detected alien civilizations, becomes even more pressing. The impossible galaxies aren't just a challenge to cosmology. They're revealing how much we still don't understand about reality itself. We began with a simple observation. Galaxies that shouldn't exist, appearing in the deepest images of space ever captured. We've journeyed through evidence that challenges every major pillar of modern cosmology. Galaxies assembling in half the expected time. Icon of supermassive black holes that grew impossibly massive. Cosmic structure organizing itself faster than physics should allow. Chemical enrichment happening in the cosmic blink of an eye. Each piece of evidence stands independently. Together, they form an undeniable pattern. Something fundamental in our understanding is incomplete. The scientific community stands at a crossroads. Continue adjusting parameters within the existing framework, hoping to accommodate the observations. Or embrace a more radical revision, acknowledging that the universe is older, or that physics operated differently in its youth, or that dark matter and dark energy are stranger than we imagined. What seems certain is that the impossible galaxies are real. They're not measurement errors. They're not statistical anomalies. They're windows into an epoch of cosmic history that behaves differently than we predicted. Perhaps most remarkably, we're living through this revolution in real time. Every few months brings new JWST observations, new impossible objects, new challenges to established models. The crisis in cosmology is deepening, not resolving. But crises in science are also opportunities. They're the moments when paradigms shift, when revolutionary ideas emerge, when our understanding of reality takes quantum leaps forward. A century ago, unexpected observations of Mercury's orbit and starlight bending near the Sun led Einstein to general relativity, a complete reconception of gravity, space, and time. A century before that, anomalies in planetary motions led to the discovery of Neptune. Today's impossible galaxies might be leading us toward a similar revolution. A new understanding of time. A new conception of how structure emerges. A deeper appreciation for the mechanisms that transform the hot, dense plasma into the rich, complex universe we inhabit. The universe has surprised us before. It will surprise us again. What matters is that we remain open to the evidence, especially when it challenges everything we thought we knew. Those impossible galaxies are still out there, still visible in JWST's images. Still massive. Still ancient. Still impossible according to yesterday's physics. But not impossible in the universe we actually inhabit. Only impossible in the universe we thought we understood. The universe is vast. The mysteries are endless. The journey continues. And we've only just begun to see what's really out there. But there's something we haven't discussed yet. Something that makes the impossible galaxy problem even more profound. Everything we've examined so far, every galaxy, every black hole, every structure exists within the observable universe. The sphere of space from which light has had time to reach us since the Big Bang. The observable universe has a radius of approximately 46.5 billion light-years. Beyond that horizon lies more universe. Potentially infinite amounts of it. Regions of space so distant that their light hasn't reached us yet and never will due to cosmic expansion. Here's the disturbing question. If structure formed impossibly fast in the regions we can see, what happened in the regions we can't? Dr. Max Tegmark at MIT has spent decades contemplating this question. The impossible galaxies in our observable region might be just the tip of something much larger, he explained in a 2024 lecture. If the same accelerated structure formation occurred everywhere, the unobservable universe might be radically different from what we've assumed. The traditional horizon problem in cosmology asks, why is the cosmic microwave background so uniform? Why do regions of space that were never in causal contact, too far apart for light to have traveled between them, have the same temperature to within 1 part in 100,000? Cosmic inflation was proposed to solve this problem. A period of exponential expansion in the first fraction of a second after the Big Bang supposedly stretched a small, causally connected region to encompass everything we see today. But the impossible galaxies suggest a different kind of horizon problem. If structure formed faster than expected in our observable universe, it likely formed faster everywhere. Across the entire expanse of space that underwent inflation together. That means there could be mature cosmic structures, galaxies, clusters, even larger formations existing in regions we'll never observe. And here's where it gets strange. Some of those regions are moving away from us faster than light due to the expansion of space itself. We'll never see light from them. We can never know what they contain. But the physics that created impossible galaxies here created similar structures there. The universe beyond our horizon might be teeming with ancient galaxies, mature black holes, and organized structure dating back to epochs even earlier than the galaxies JWST is finding. We're discovering that the universe in our neighborhood developed faster than expected. The implication. The universe as a whole is more evolved, more structured, more complex than our models predicted. Let's return to the timeline. According to standard cosmology, the universe went through several distinct epochs. The Big Bang itself. Then the Planck epoch, the Grand Unification epoch, the Electroweak epoch, each one lasting fractions of a second as the universe cooled and fundamental forces separated. Then came inflation. Then the production of matter and antimatter. Then the formation of protons and neutrons. Then Big Bang nucleosynthesis, the creation of hydrogen and helium. Then, the Dark Ages. Hundreds of millions of years where nothing happened. The universe just expanded and cooled. No stars. No light. Just hydrogen and helium floating in darkness. Or so we thought. The impossible galaxies suggest the Dark Ages might not have been so dark. Or perhaps they weren't as long as we calculated. Something was happening during those supposedly quiet centuries, something that allowed structure to jumpstart earlier than predicted. Dr. Rannan Barkana at Tel Aviv University proposed a controversial idea in early 2024. What if the Dark Ages contained processes we haven't considered? What if dark matter was interacting in ways that pre-assembled structure before the first stars even ignited? His models suggest that dark matter might have been collapsing into halos and pulling normal matter with it much earlier than standard simulations predict. By the time the first stars turned on at 100 to 200 million years after the Big Bang, the groundwork for galaxy formation was already in place. The universe didn't pause. It was preparing. This brings us to one of cosmology's most fundamental questions. What were the first luminous objects in the universe? Standard models predict population 3 stars, massive, pure hydrogen-helium stars that lived fast, died young, and scattered heavy elements through supernova explosions. JWST was designed partially to find these pristine first stars. But so far, it hasn't found a single one. Every early galaxy discovered shows evidence of stellar populations already enriched with heavy elements. Every spectrum reveals carbon, oxygen, nitrogen elements that require previous generations of stars to exist. Where are the population 3 stars? One possibility. They existed so briefly that JWST's observations missed them. They might have ignited, lived their few million-year lives, and exploded before the epochs JWST is observing. But another possibility is more unsettling. What if population 3 stars were never the dominant first objects? What if something else lit up the early universe? Dr. Fabio Pacucci at Harvard proposed an audacious alternative. What if the first luminous objects weren't stars at all, but rather supermassive black holes? If primordial black holes formed in the first seconds after the Big Bang, Pacucci argued, they could begin accreting matter immediately. Within a few million years, they'd be massive enough to ignite as quasars, incredibly bright objects that could ionize vast volumes of space around them. In this scenario, quasars came first. They created ionized bubbles in the neutral hydrogen filling space. These bubbles provided ideal conditions for the first stars to form. The ultraviolet radiation from quasars helped cool the gas, allowing it to collapse more efficiently. The impossible black holes JWST discovered might not be outliers at all. They might be the most common type of early massive object, with galaxies forming around them rather than the other way around. This completely inverts our understanding of cosmic history. Instead of galaxies forming first and then growing black holes in their centers, black holes form first and galaxies assemble in their gravitational wells. It would explain why every early massive galaxy has a supermassive black hole. It would explain why these black holes are so large so quickly. And it would explain where the population 3 stars went. They never dominated the early universe because quasars beat them to the punch. This alternative timeline has profound implications for cosmic reionization, the epoch when the first light sources ionized the neutral hydrogen filling space. Standard models predict reionization completed by about 1 billion years after the Big Bang, driven primarily by ultraviolet light from the first galaxies. But observations of the cosmic microwave background suggest reionization might have begun much earlier, perhaps as early as 250 million years after the Big Bang. JWST's discovery of massive, active galaxies at 300 million years supports early reionization. But there's a problem. The number of early galaxies isn't quite sufficient to ionize all the hydrogen in space by themselves. Something else contributed. Perhaps primordial quasars. Perhaps population 3 stars that JWST hasn't yet detected. Or perhaps something we haven't imagined. In September 2024, a team analyzing JWST data found indirect evidence of reionization occurring in patches, regions of ionized space surrounded by neutral hydrogen. The pattern suggested localized sources of intense radiation, consistent with rare, extremely bright objects rather than distributed starlight. Here's another cosmic mystery that the impossible galaxies illuminate. The missing baryons problem. Baryons are normal matter, protons and neutrons, the stuff that makes up atoms. Big Bang nucleosynthesis precisely predicts how many baryons should exist. About 5% of the universe's total mass energy. But when astronomers count up all the baryons they can find in stars, in gas clouds, in the intergalactic medium, they only account for about 3%. Where's the other 2%? For years, astronomers suspected the missing baryons were hiding in hot, diffuse gas between galaxies, too hot to emit easily detectable radiation, but warm enough to be ionized. In 2020, observations confirmed this suspicion. Fast radio bursts passing through intergalactic space were delayed by exactly the amount expected if hot, ionized gas filled the voids between galaxies. The impossible galaxies reveal that structure formed earlier and more efficiently than expected. That means the intergalactic medium was disturbed earlier, heated earlier, ionized earlier. This should leave signatures in the cosmic microwave background, subtle distortions caused by energetic processes in the first few 100 million years. And indeed, some research groups claim to have detected anomalies in the CMB that aren't explained by standard models. If confirmed, these anomalies suggest that energy injection into the early universe was more vigorous than predicted. Something was heating and ionizing gas throughout space during the supposedly dark ages. The impossible galaxies, the missing baryons, the CMB anomalies, they're all pieces of the same puzzle. The puzzle extends beyond electromagnetic observations into the gravitational wave spectrum. LIGO and Virgo detect gravitational waves from merging black holes and neutron stars. But these events occur in the relatively nearby universe. To observe the earliest black hole mergers, those occurring in the first billion years after the Big Bang, we need more sensitive instruments. The Laser Interferometer Space Antenna, LISA, scheduled to launch in the 2030s, will detect gravitational waves from supermassive black hole mergers. If the impossible black holes JWST discovered are common, LISA should detect gravitational waves from their formation and early growth. But here's the prediction that has gravitational wave astronomers excited. If primordial black holes formed in the first seconds after the Big Bang, their collisions and mergers should have created a stochastic gravitational wave background, a faint hum of spacetime vibrations permeating the universe. In 2023, multiple pulsar timing arrays announced they had detected hints of such a background. The signal was stronger than expected from conventional sources like distant supermassive black hole mergers. Could this be evidence of primordial black holes colliding throughout cosmic history? If so, it would support the hypothesis that these objects dominated the early universe, explaining both the gravitational wave background and the impossible black holes JWST discovered. The pieces are connecting across different observational domains. There's yet another piece of evidence, this one coming from quasar spectroscopy. When we observe distant quasars, their light passes through vast stretches of intergalactic space before reaching us. Neutral hydrogen along the way absorbs light at a specific wavelength called Lyman alpha, creating a forest of absorption lines in the quasar's spectrum. The Lyman alpha forest provides a map of hydrogen distribution across cosmic history. Dense regions create strong absorption lines. Sparse regions create weak ones. In 2023, astronomers analyzing quasar spectra from the Sloan Digital Sky Survey noticed something odd. The Lyman alpha forest at high redshifts, corresponding to early cosmic times, showed more structure than predicted. The absorption patterns suggested hydrogen was distributed more unevenly than models expected, clumped into denser regions with emptier voids between them. This implies matter was already organized into structures earlier than the standard timeline allows. Independent confirmation came from JWST observations of background galaxies whose light passes through the early intergalactic medium. The absorption patterns matched the Sloan data. Too much structure, too early. Dr. Martin Hainault at Cambridge, an expert in intergalactic medium physics, called it another nail in the coffin of the standard structure formation timeline. The hydrogen distribution is telling the same story as the impossible galaxies. Organization happened faster than we thought possible. We must return to the cosmic microwave background, the most precisely measured object in cosmology and the foundation of the Standard Model. The Planck satellite mapped the CMB with exquisite precision, measuring temperature fluctuations to within millionths of a degree. These fluctuations reveal the density variations in the early universe that eventually grew into galaxies and galaxy clusters. The Planck data matches lambda-CDM predictions extraordinarily well. This is why the impossible galaxy problem is so vexing. The CMB suggests one timeline while JWST observations suggest another. But the Planck data isn't perfect. Several anomalies have persisted through multiple analyses. The cold spot, a region of the CMB about 10 degrees across that's significantly colder than surrounding areas. It shouldn't exist in standard inflation models, yet there it is. The hemispherical asymmetry, one half of the sky shows slightly larger temperature fluctuations than the other half. The universe should be statistically isotropic, but it's not quite. The low quadrupole, the largest scale temperature fluctuations are weaker than predicted. This suggests something unusual about the universe's properties on the largest scales. The axis of evil, a bizarre alignment of multiple multipole components in the CMB that shouldn't correlate, yet they point in roughly the same direction. For years, cosmologists dismissed these as statistical flukes or instrumental artifacts. But they've survived rigorous analysis. They're real. Could they be related to the impossible galaxy problem? Some researchers think so. In late 2024, Dr. Eleonora D. Valentino at Durham University published a provocative paper connecting the CMB anomalies to JWST's discoveries. Her argument: all the anomalies might stem from the same cause, an additional energy component in the early universe that existed only briefly during the first few 100 million years. This component, whether it's early dark energy, a new field, or modified gravity, would affect both the CMB, creating the observed anomalies, and structure formation, allowing impossible galaxies to form quickly. We've been treating these as separate puzzles, D. Valentino explained. The CMB anomalies, the Hubble tension, the impossible galaxies, the too early reionization, the Lyman alpha forest structure. But what if they're all symptoms of the same new physics operating in the early universe? Her models show that a field that contributes about 10 to 15% of the universe's energy density between 100 million and 500 million years after the Big Bang could simultaneously create the observed CMB anomalies through its effect on acoustic oscillations, accelerate structure formation, producing the impossible galaxies, raise the early expansion rate, contributing to the Hubble tension, enhance gravitational clustering, explaining the Lyman alpha forest structure, increase the ionization rate, enabling early reionization. One cause. Multiple effects. All observed. The model is speculative, but it's testable. Future observations can confirm or rule out specific predictions. A completely different explanation comes from considering our cosmic address. What if we're not in a typical region of the universe? What if we live in or near a massive cosmic void, a region where matter density is lower than average? If Earth sits inside or near a void several 100 million light-years across, it would affect our observations in subtle ways. Light from distant objects would traverse regions of different density, affecting redshift measurements. Local measurements of the Hubble constant would differ from measurements based on the CMB. And here's the kicker. If we're in a void, objects at high redshift might be closer than we think. The galaxies JWST observed might not be as early as their redshifts suggest.
Space between them.
They might have had more time to form than we calculated.
You know they're there because you can see their effects.
This void hypothesis has gained attention as a possible solution to the Hubble tension.
The coffee cup
in
hovering
2023,
in midair,
several research groups presented evidence that the local universe, within 300 million light-years, has slightly lower density than the cosmic average.
Every star,
but
every
extending
galaxy,
this to solve the
every
impossible
nebula
galaxy
captured by
problem
our most
requires a void of
powerful
implausible
telescopes
size, perhaps
represents
a billion
less
light
than
years across.
15% of what's actually
And
out
even
there.
then, it struggles to
rest?
fully explain
It's
the
made of something
observations.
that doesn't emit light,
Most
doesn't
cosmologists
absorb right,
consider the
and
void
doesn't
hypothesis
interact with
unlikely to be the
electromagnetic
complete
radiation
answer.
in any way we can
But it
directly
remains a
measure.
possibility that can't
Yet
be
it
entirely
shapes
dismissed.
everything. It
Perhaps
holds
the most
galaxies
radical
together.
solution
It
abandons
bends
the idea
fabric
of a single
space
Big Bang
itself.
entirely.
Without it, you wouldn't
Cyclic
exist.
universe models
Without
propose
it,
that the Big Bang
galaxies
wasn't
would
the
tear
beginning,
themselves
but rather a
apart.
transition
Stars
from a
would never
previous
form,
cosmic epoch.
and the cosmic web that
The universe
structures
might
our
undergo
entire
infinite
universe
cycles of
would
expansion and
collapse into
contraction,
chaos.
or might be part of
We
a larger
call it dark
multiverse structure
matter.
where new
But that
universes
name
continually
barely
bud off
scratches
from
the surface
existing
of how
ones.
strange, how pervasive,
In Roger
and
Penrose's
how
conformal
fundamentally
cyclic
important
cosmology,
this
our
invisible
universe emerged
substance
from
really
the
is.
infinitely expanded,
Today,
death state
we
of a
journey
previous
through
universe.
evidence that challenges
The
everything
Big Bang
we thought
was
we
a
knew
transition
about the
point,
composition
not an
of
absolute
reality
beginning.
itself.
In
Prepare
Paul
yourselves.
Steinhardt and Neil
We
Turock's
begin.
ekphorotic model,
If
our
you're
universe
enjoying the
resulted
video,
from the
feel
collision of
free to
two
tap
higher
that
dimensional
like
brains
button.
in a bulk
It shows
space of
me
extra
this content
dimensions.
sparks something in you.
Each collision
And if
starts
you'd like
a new
to stay
cycle.
close as new stories
These
appear,
models can
subscribe to
potentially
the channel.
explain the impossible
It
galaxies
genuinely
by
means a
allowing
lot
more time
and
or
helps this
different
place
initial
grow in the
conditions
right
than
direction.
standard Big Bang
Thank you for
cosmology
being here.
permits.
In 1933,
Perhaps our universe
a Swiss
inherited
astronomer
structure
named
or
Fritz
conditions from a
Zwicky
previous
pointed the
epoch.
telescope at Mount Wilson
Perhaps the initial
Observatory toward
conditions
the Coma Cluster,
13.8 billion
a
years ago
massive
weren't
collection
truly
of
initial.
over 1,000 galaxies
models face
located
significant challenges.
320 million light years
They must
from Earth.
explain why the
What he
CMB
was
looks
about
like
to
it came
discover
from a
would
hot Big
haunt
Bang.
physics for nearly a
They
century.
must account for entropy
Zwicky was
accumulation
measuring the
across
velocities
cycles.
of galaxies within the cluster.
They must make
watching
testable
how fast
predictions
they
that
moved
distinguish
relative to
them
each
from
other.
standard
He
cosmology.
applied a straightforward calculation,
But they represent
one
serious
that Newton
theoretical
himself would have
attempts to
recognized.
explain observations
Measure
that
the mass
don't
of the
fit
cluster
conventional
based on the
frameworks.
visible galaxies, then
At the deepest
determine
level,
if the
the
gravitational
impossible
pull was
galaxy problem
sufficient
might
to
be
keep these
revealing
galaxies
something
bound
about the
together.
nature of space-time
The
itself.
numbers didn't work.
Both
The
general
galaxies were
relativity
moving
and quantum
far too
mechanics have
fast.
been
At the
spectacularly
speeds Zwicky
successful
measured,
within their
they
domains.
should have been flung out of the
But
cluster
they're
long
fundamentally
ago,
incompatible.
scattered across the cosmos like
Efforts
stones
to
from a
create a
broken
quantum theory of
slingshot.
gravity, string
Yet
theory,
there they
loop quantum
were,
gravity,
orbiting
causal
together
set
in
theory, and
gravitational
others
harmony.
suggest that
To
space-time itself
explain what
might
he
not
was
be
seeing,
fundamental.
Zwicky calculated that the
What if
Coma cluster
space-time is
needed
emergent?
to be 400 times
What if it
more
arises
massive
from
than what was
something more
visible?
basic, quantum entanglement,
400 times more
computational
massive.
processes, or structures we
Zwicky
haven't
proposed
discovered
something
yet?
radical. There
In this
must
view,
be
time might not flow
dark
uniformly at all
dark matter,
scales.
invisible mass
The chronology
filling
we
the cluster,
perceive from the
providing
CMB
the
to the present might
gravitational
not
glue
reflect the
holding
actual
everything
causal
together.
structure of cosmic history.
The astronomical community
The events we
largely
observe as
dismissed his
sequential
findings.
might have been parallel
How could
or even reversed at a quantum level.
99.75% of a galaxy
Dr.
cluster be invisible?
Carlo Rovelli,
The idea
a founder
seemed
of loop
absurd,
quantum
a
gravity,
mathematical
suggested
error
in a
and
2024
observational
lecture.
mistake. But
The
Zwicky's
impossible
observations
galaxies
were
might
correct.
be impossible only because
For
we're trying to
decades,
understand
dark
them
matter
within a
remained a
classical
curiosity,
space-time framework.
an unexplained anomaly
Once
that
we
most
understand
astronomers
quantum gravity,
preferred to
the
ignore.
timeline problem might
Then,
dissolve.
in the 1970s,
This
a
is
young
highly
astronomer
speculative.
named Vera Rubin
We don't
began
yet have a
studying
complete
something
theory
closer
of
to
quantum
home,
gravity.
the rotation of spiral
But the
galaxies.
possibility remains
When
that
you
our
watch a
entire
spinning
conception of
carousel,
cosmic
the
chronology,
forces on
based
the
on classical
outside
general
move faster
relativity,
than those
breaks
near
down
the
at the
center.
extreme
They
conditions
have to
of the
cover
early
more
universe.
distance in the same amount
A
of
final,
time.
deeply
Our
strange
solar
possibility
system
emerges
works
from
the same
considering
way.
the universe as an
Mercury
information processing
screams around the
system.
sun at 47
Quantum
kilometers
information
per
theory
second,
suggests the
while
universe has
Neptune,
finite information
30 times
content
farther
limited
out,
by the
plods
Beaconstein
along
bound
at
and
just
related
5
principles.
kilometers per second.
The information
This is how
capacity
gravity
of a region
works.
of space scales
The farther
with its
you
surface
are
area,
from the
not
source
its
of
volume.
gravitational pull, the
If
slower
information
you
is
should orbit.
fundamental and matter/energy are
Rubin
emergent from
expected to see
information
the same
processing,
pattern
then
in
structure
spiral
formation
galaxies.
might work differently
Stars
than we
near
think.
the galactic center should
Dr.
orbit quickly, while stars
Zlatko
in the
Biebrel
outer
at Oxford
regions
has
should move
proposed that the
much more
universe
slowly.
might optimize for
She
rapid
pointed her
information
telescope
generation.
at galaxy after
Structures
galaxy,
that create and process
meticulously
information,
measuring
stars,
the rotation
galaxies,
speeds of stars
eventually
at
life and
various
intelligence
distances
might
from
be favored
each
by
galactic
fundamental
core.
physical
What
principles
she
we don't
found
yet
made
understand.
no sense.
The
The
impossible
stars at
galaxies
the edge
might
of
not be
galaxies were
impossible
moving
at all.
just as
Biebrel
fast as
suggested.
stars near the center.
They might
In
be
some
optimal
cases, they were
solutions to
moving
an
even
information
faster.
maximization problem.
According to Newton's laws,
The universe
according to
organized
everything we
itself
understood
quickly
about
because
gravity,
rapid organization
these outer
generates
stars
more
should have been
information,
flung
and
into
information
intergalactic
generation
space
is what the
billions
universe
of
wants
years
to
ago.
maximize.
But they weren't.
This perspective
Rubin
draws
had
on
discovered
ideas from
rotation
digital
curves
physics,
that remained
from bit
flat
theory,
across
and
entire
computational
galaxies,
universe hypotheses.
defying every prediction of
It's at the
gravitational
frontier of
physics.
speculation,
She
but it offers a
calculated the
completely
mass
different different
required
lens
to
for
explain these
understanding why
rotation
structure
speeds.
forms faster
The
than
results were
classical models
staggering.
predict.
Galaxies must
All of this
contain
theoretical
5 to
physics
10
in
times
cosmology
more
has a
mass than we
profoundly
can
human
see.
dimension.
And this invisible mass
If galaxies
wasn't
formed
concentrated in
earlier
the
than
galactic
expected,
core.
then
It
stars
extended
formed earlier.
far beyond the visible edges,
And if stars
forming
formed earlier,
vast
then
spherical
planets
halos
formed
around
earlier.
each galaxy.
And if
The
planets
evidence
formed
was
earlier, then
undeniable.
life could have started
Zwicky's
earlier.
dark matter wasn't an anomaly
earlier.
in one distant cluster. It
Consider.
was everywhere. But
Our
what
Sun is
was
a
it?
third-generation star,
Astronomers
formed about
searched for
4.6
conventional
billion years ago
explanations.
from material enriched
Perhaps
by
dark
previous
matter
stellar
was simply
generations.
ordinary matter that didn't
Earth
emit
followed
light.
shortly after.
Dead stars, black
Life
holes,
appeared within a few
cold
hundred
gas
million
clouds,
years of
brown
Earth's
dwarfs,
formation.
planets floating between the
Intelligence
stars.
took about 4 billion
They
years
called
from the
these
first
objects
single-celled
machos,
organisms.
massive,
But
compact
the impossible
halo
galaxies
objects.
reveal that stellar
Throughout
generations
the
were cycling
1990s,
much earlier than we
astronomers
thought.
conducted extensive surveys,
Heavy elements, the
watching
carbon,
for the
oxygen,
telltale signs
iron,
of
silicon
machos
necessary
passing
for
in front
rocky
of
planets
distant
and
stars.
organic chemistry
When
were
a
being
massive
produced in
object
large
passes
quantities by
between us
500
and a
million
star,
years after
its
the Big
gravity
Bang.
bends the starlight,
The first
causing the
potentially
star to
Earth-like planets
temporarily
might have
brighten,
formed by 1 to
a
2 billion
phenomenon
years
called
after the Big
gravitational
Bang.
microlensing.
That's 11
They
to
found
12
some
billion
machos,
years ago.
but nowhere near
If life
enough.
follows chemistry with
Ordinary
the same
matter,
speed elsewhere
even
that
dark
it followed
and
on
cold,
Earth,
could
the first
account for
living
only a
organisms
small
could have appeared
fraction
10
of
to
the missing
11 billion
mass.
years ago.
Dark matter,
The first
whatever it
intelligence
was,
could have
had to
emerged
be
6
something
to 7
truly
billion years
exotic,
ago.
something that had never been
Civilizations
directly
billions of
detected
years more
in
advanced
any
than
laboratory
humanity
on
might
Earth,
exist or might have
something that
existed.
represented a fundamental
This makes the
component
Fermi
of reality
paradox, the
that
puzzle of
physics
why we
had
haven't
completely
detected alien
overlooked.
civilizations,
But
even
the
more
evidence
pressing.
forces us to confront
If the
an
universe has
uncomfortable
been capable of
possibility.
supporting life
We
for
are
11
made of the
billion years
universe's
rather than the 8 to
minority
9 billion
constituent,
years we
living
previously
in a
thought,
cosmos
where is everyone?
dominated by something we
A
cannot
civilization
see,
with a 6
cannot
billion year
touch,
head
and
start
do
on
not
humanity should be
understand.
incomprehensibly
If dark
advanced.
matter truly exists
They should have
as an
colonized
invisible
their galaxy.
substance pervading the universe,
Potentially
it
many
should leave
galaxies.
signatures, fingerprints
They should
in
have
the
left
cosmic
detectable
structure
artifacts,
that
Dyson
only
spheres,
its presence
altered
could
stars,
create.
engineered structures
Scientists
visible across
discovered the
cosmic
first
distances.
signature in the most violent
Yet we
events
see
in the
nothing.
universe, galaxy
The
cluster
universe
collisions.
appears empty.
In 2006,
Silent.
NASA's Chandra
The
X-ray
impossible
Observatory
galaxies
captured
suggest
images
life
of
should
the
be
bullet
common and
cluster,
ancient.
two galaxy
The
clusters
apparent
that had
absence of
slammed
that light
into each other
becomes
at
even more
millions
mysterious.
of kilometers per hour.
Perhaps
The collision
intelligence is
occurred
incredibly rare,
3.8
so rare that
billion years
despite
ago,
the vast number
and the
of stars
aftermath
and the
revealed
extended time
something
available,
extraordinary.
we're among the first.
When the clusters
The
collided,
great filter might
their
lie behind
ordinary
us,
matter,
not ahead.
primarily hot gas,
Or perhaps
glowing in
advanced
X-rays,
civilizations exist but are
interacted
invisible
and
to us,
slowed
either
down,
hiding deliberately,
creating a shock
existing
wave
in
of
forms we can't
superheated
detect,
plasma
or
between the
operating on
clusters.
scales we can't
You
perceive.
can see this glowing cloud
Or perhaps
in X-ray
the universe
images,
is young enough
marking
that
where the
intelligence
visible
is just
matter
now
piled
beginning
up
to
during the
emerge across
collision.
multiple
But
worlds.
gravitational
We
lensing
might be
revealed
part of the
something
first
else
wave.
entirely.
The
Astronomers
possibility of
mapped the
ancient alien
gravitational field
civilizations
by
has given
observing
rise
how
to a new
light
field.
from background galaxies was bent
Archaeological
and
astronomy,
distorted.
the search for
The gravitational
technosignatures from
center,
extinct
the location
civilizations.
of most of the mass,
If a
wasn't where
technological
the hot gas
civilization
was.
arose 5 billion
It had
years ago
passed
in a galaxy
right
now
through the
billions of
collision
light
point,
years away, we
separating
might
from
see
the
light from
ordinary
their
matter
prime,
by
their
more
Dyson
than 3
spheres, their
million
megastructures,
light-years.
their galaxy-spanning
This is the
activities,
signature
even though
of
the
dark
civilization
matter.
itself might
While
be long
ordinary
gone.
matter interacts, collides,
JWST
and
and
slows
future
down through
telescopes aren't just
electromagnetic
looking for
forces,
natural cosmic
dark
phenomena.
matter passes through everything
They're also
like a ghost
intentionally
through
or not
walls.
scanning for
It's
artificial
collisionless,
structures.
interacting only
Some
through
of the
gravity.
impossible objects
The
might
bullet
not be
cluster
galaxies at all.
represents just one piece
They
of a
might
much
be
larger
engineered
puzzle.
structures so vast that they
Scientists
mimic
have now
natural
observed
objects when
dozens
viewed
of
from
colliding
cosmic
clusters,
distances.
and every single
This
one
idea
tells the
sounds
same
like
story.
science fiction.
The gravitational mass
But it's
center
being taken
separates from the
seriously by
visible
a
matter
growing
during
number of
collisions.
astronomers.
But perhaps the
In
most compelling
2024,
evidence comes
several
from something
papers
called
outline
baryon
specific search
acoustic
strategies for
oscillations,
detecting ancient
pressure waves
megastructures
that
in
ripple through the early
JWST data.
universe. In the
DR.
first 380,000
Jason
years
Wright
after
at
the
Penn
Big
State,
Bang,
who leads
the
the
universe was a
glimpsing heat
hot,
from Alien
dense
Technologies
plasma.
Project,
Ordinary
explained.
matter, protons,
If
neutrons,
advanced
electrons,
civilizations are common
everything
and
that would
long-lived,
eventually form
statistical
stars and
arguments
planets and
suggest we
people
should see their
was coupled
artifacts.
to photons,
The
creating a
impossible
fluid that could
galaxies
transmit
database
pressure
is
waves
large
like
enough that
sound
even
waves
rare
through water.
technosignatures might be
Dark
present.
matter, unable to interact
need
with
to look
photons,
carefully.
remained unaffected
The
by these
rapid formation of
oscillations.
structure in
When
the
the
early
universe
universe
cooled
also
enough
has
for atoms
implications
to
for the
form,
far
the
future.
pressure waves froze
Physicist
into the
Frank Tipler
distribution of
proposed
matter,
the omega point
creating a
hypothesis, the
characteristic
idea that
pattern of
intelligence might
galaxy
eventually
clustering
spread
with a
throughout the
specific
universe,
scale,
continuing until the final
approximately
moments before the
500
big
million
crunch or
light
heat
years.
death, and in doing so,
Astronomers have
processing an
measured this
infinite amount
pattern
of
in the
information in
distribution of
finite time
galaxies
through ever
across
faster
billions of light
computations.
years of space, and
Its
it
structure
matches
forms quickly,
theoretical
yet the
predictions
universe
with
is biased
stunning
toward
precision.
complexity. Perhaps
Here's
this
what
isn't
makes
just
this evidence
speculation
so
but inevitable
powerful.
destiny.
The pattern we observe
Consider.
requires dark matter to have
The
existed
impossible
in the early
galaxies
universe
reveal that the
at a
universe
ratio
organized
of
itself from
approximately
chaos
5
to
to 1
structure faster
compared to
than
ordinary
expected.
matter. 5
Stars,
parts dark
planets,
matter, 1
perhaps
part
life followed
ordinary
quickly.
matter. This ratio
Intelligence
determines
emerged.
the amplitude and wavelength
Now
of the
that
acoustic
intelligence is beginning
oscillations,
to understand
and any
and manipulate
significant
the
deviation
cosmos.
would create a completely
Perhaps
different
this is a
pattern in
pattern that
galaxy
repeats across the
distribution.
universe, matter
We
organizing,
observe the
life
predicted
emerging,
pattern.
intelligence
The ratio
arising,
holds.
and eventually
The
intelligence
evidence
taking
converges
control
from
of cosmic
completely
processes
independent
themselves.
measurements made across
The far
vastly
future
different
might not
scales
be a
and cosmic
gradual heat
epochs.
death but rather a
But
takeover
this
by
represents
intelligence,
just
biological
one
or
piece
artificial,
of a
that
much
spreads
larger
across
puzzle
galaxies,
hidden
manipulating
in the
stars
oldest
and
light
black
in the
holes,
universe,
eventually
the
shaping the
cosmic
universe's
microwave
evolution
background.
itself.
The cosmic
This is deeply
microwave
speculative.
background, the CMB,
But if the universe's
is the
history shows
afterglow of the Big
acceleration
Bang,
toward complexity,
light that has
why
been
wouldn't that
traveling through
trend continue?
space for 13.8
Zoom back from
billion
cosmic
years.
scales to the human scale.
This light carries within
To you,
it a
watching
detailed
this,
snapshot of the universe
what do the
when it was
impossible
just
galaxies mean for your life?
380,000 years old,
They reveal that
encoding
we live in a
information
universe
about
stranger
every
than we
component of
imagined.
cosmic composition.
More ancient,
When the European Space
more
Agency's
complex,
Planck satellite mapped
potentially
the CMB
more
with
hospitable to life and
unprecedented
intelligence
precision,
than we thought.
it measured tiny
They
temperature
suggest that the
fluctuations,
story of the cosmos is
variations
still
of
being
just
written,
a few millionths of a degree.
that our understanding
These
is incomplete.
fluctuations represent the
That
seeds
major
of all
revolutions
cosmic
in
structure,
physics might lie
the
ahead.
quantum fluctuations
They
that would
demonstrate
eventually
that
grow
asking
into
simple
galaxies,
questions, when did the
clusters,
first
and
galaxies
the cosmic
form,
web.
can uncover profound
The
mysteries
pattern
that
of these
challenge our
fluctuations
deepest
depends
assumptions about
critically
reality.
on the ratio of dark matter
they remind
to
us of
ordinary
something
matter
essential.
in the early universe.
We don't have
Planck's
all the
measurements
answers.
allowed scientists to
The
determine
universe
the
continues
composition
to
of the
surprise
universe
us.
with extraordinary
Every
precision.
new observational capability reveals
68.3%
phenomena
dark
that
energy,
defy our models.
26.8%
This is
dark
cause
matter,
for
and
humility,
just 4.9%
but also for
ordinary
wonder.
matter. Everything
We
we've
live
ever
in an era
seen,
where
everything
humanity's
that makes
most
up
sophisticated
Earth, the sun,
instruments are peering
all
into the
visible
earliest
stars and
moments of
galaxies,
cosmic history,
less than 5% of what
where we
exists.
can detect light that traveled
But the
for
most
13
remarkable
billion years to
discovery
reach our
involves
eyes.
what happened in the early
Where
universe
we're asking
because of
questions
dark
our
matter's
ancestors
unique
couldn't have
properties.
imagined, and getting
In the
answers
first
that
few
surprise even
100,000
us.
years after the Big Bang,
The impossible
ordinary matter
galaxies
was
are out there
trapped
right
in an
now.
electromagnetic dance with
Real
photons,
objects in real space.
unable to collapse under its own
Their
gravity.
light streaming through
But
the
dark
void,
matter,
carrying
immune to
information about
electromagnetic
conditions
forces,
in the infant
began
universe.
collapsing immediately,
That light
forming
reaches our
gravitational
telescopes,
potential wells.
becomes
Think
data,
of it like this.
gets
Dark matter
analyzed by
created
scientists
invisible
trying to understand
scaffolding,
what it means.
gravitational wells that
And
ordinary
slowly,
matter
piece by piece,
eventually
we're
fell
figuring
into
it out.
once the universe cooled
Maybe
enough
we'll
for atoms
discover
to
the
form.
universe is older
Without
than we
this
thought.
head start, without dark matter
Maybe we'll
creating
find that dark
structure
matter is
before
stranger.
ordinary matter could, the
Maybe we'll
universe would
realize
look
that time itself
fundamentally
doesn't
different.
work the way we
Galaxies
assumed.
would have formed billions of
Whatever
years
the
later,
answer,
if
we're
at all.
getting closer.
The cosmic web of
We've
structure we
traveled
observe
through layers
would
of
not
evidence that
exist.
challenge the foundations
Computer
of cosmology.
simulations confirm this. When
We've examined
scientists model
competing
cosmic
theories and
evolution
radical
without dark
proposals.
matter, using only
We've
ordinary
considered
matter and
implications
gravity,
ranging
the
from the nature
resulting
of time
universe
itself to the
bears
destiny
no
of
resemblance
intelligence
to what
in the
we
cosmos.
observe. Galaxies
The
don't
impossible
form in the right
galaxies
places
stand as
at the right
monuments to
times
our
or in
incomplete
the right
understanding.
numbers. The structure is
They're
simply
not
wrong.
problems to be explained
But
away.
when they add dark matter in
They're
the
doorways
precise
to deeper
proportions
truth.
measured by Planck, matching
Science
the
advances
rotation
not
curves
through
Vera
confirming
Rubin
what we
observed,
already believe,
matching the
but through
gravitational
discovering what we
lensing
got
seen
wrong.
in cluster collisions,
The
matching the
impossible
acoustic
galaxies are telling
oscillations in
us we got
galaxy
something
surveys,
wrong, something
suddenly
fundamental
the
about how the
simulations
universe
produce a
organized
universe that
itself
looks
in its
almost
youth.
identical to our own.
The next decade will
The
be
evidence
crucial.
extends beyond cosmic structure
JWST continues
into the
its
realm
observations,
of individual
pushing
galaxy
deeper into
formation.
cosmic history.
Astronomers have
New
discovered
telescopes come
ultra-faint
online,
dwarf
bringing
galaxies
unprecedented
orbiting the Milky Way.
capabilities.
Tiny galaxies
Theoretical
containing just a
physicists
few
develop new
thousand
models,
stars,
seeking
but
frameworks
with
that
masses
can accommodate
indicating
all
they're
the
almost
observations.
entirely made of dark matter.
We might be on the verge
sometimes
of a
with
new
ratios
cosmic
exceeding
paradigm.
1,000 to 1.
A revised understanding
These
of structure
galaxies
formation,
are dark
of
matter,
dark matter's
with just a
properties,
sprinkle
of how
of ordinary
time and
matter,
space function at
like
extreme
finding a
scales.
cloud you can almost touch.
Or we might discover
They
something
exist
even
at the
more
very
profound, that
edge
the
of
universe
detectability,
itself is more
visible
varied,
only
more
because
complex,
of those
more
few
surprising
thousand
than our
stars
current
embedded
frameworks can
in
capture.
massive dark matter halos.
Either way, the
And
journey
here's what
continues.
makes them so important.
The universe
Their
doesn't care
existence
about
was
our models
predicted
or
by
our
dark matter
theories.
simulations
It
before they were
simply is
discovered.
what it is.
The theory said
Our
these
task is
ultra-faint
to observe
galaxies
carefully,
should
think
exist,
clearly,
orbiting
and revise
larger
our
galaxies in
understanding when
specific
observations
numbers and
demand it.
distributions.
The
When
impossible
astronomers looked
galaxies are
carefully
doing
enough,
exactly
there
that,
they
forcing
were,
us to revise,
exactly where the
reconsider,
simulations
reimagine
predicted.
what's possible.
The evidence extends
And in doing
beyond
so,
what we can
they're
see
teaching us the
into the
most
realm of
important
what we
lesson in
cannot
science.
see. Dark matter
Stay
may
humble,
be
stay
influencing
curious,
the very
and never
fabric of
assume you've
space-time
figured everything
in
out.
ways we're only beginning
Because
to
the
detect.
universe always
So
has more
what
surprises
is dark
waiting.
matter actually? What
The
could
objects that
possibly
broke our
explain
understanding
all
are
these
still there,
observations
billions of
while
light years
remaining
away.
invisible and intangible?
Still massive.
The leading
Still
theory
ancient.
suggests dark matter consists
Still
of
impossible
WIMPs,
according to
weakly
yesterday's
interacting massive particles.
But possible in the
These
universe
are
we're learning
hypothetical
to see
particles
clearly.
that interact only through
cosmos
gravity
is
and
vast.
possibly the weak nuclear
mysteries
force,
are endless.
one of the four fundamental
And we've
forces
never
of nature.
been closer to
They
understanding
don't
some of the
interact
deepest
with
questions about
electromagnetic
existence
radiation,
itself.
which is why they're invisible.
The journey
They don't
continues.
interact with ordinary matter through any
adventure
force
goes on.
except gravity, which
And
is
the
why they
universe
pass
keeps
through
teaching us
everything.
that reality is stranger, more
According to
wonderful,
calculations
and more
by
profound
physicists
than we
at
ever
CERN
dared
and
imagine.
laboratories around the world, WIMPs should have masses somewhere between 10 and 1,000 times the mass of a proton. They should be moving through space at velocities of a few hundred kilometers per second left over from the Big Bang. And they should be everywhere. Right now, as you process these words, approximately 100 billion dark matter particles are streaming through your body every second. They pass through the Earth as if it were empty space, emerging on the other side completely unaffected. Occasionally, perhaps once in a decade for any given particle, one might collide with an atomic nucleus in your body, transferring a tiny amount of energy before continuing its journey. This is why detecting dark matter is so extraordinarily difficult. Scientists have built detectors deep underground, shielded from cosmic rays and radioactive background, filled with ultra-pure materials cooled to near absolute zero, waiting for that rare collision between a WIMP and an atomic nucleus. The most sensitive experiment, Xenon 1T in Italy, uses 3.2 tons of liquid xenon surrounded by photomultiplier tubes that can detect even a single photon of light. After years of operation, accounting for cosmic rays, radioactive contamination, and every other possible source of interference, they've detected nothing conclusive. This forces us to reconsider fundamental assumptions about what dark matter might be. Perhaps WIMPs aren't the answer. Perhaps dark matter consists of axions, hypothetical particles a trillion times lighter than electrons, with properties so unusual they barely qualify as matter in any conventional sense. Or perhaps dark matter is primordial black holes, formed in the first fraction of a second after the Big Bang, too small to have been detected, but numerous enough to account for the missing mass. Or perhaps, and this is where the implications become truly profound, dark matter represents a window into physics beyond the Standard Model, the theoretical framework that describes all known particles and forces. Every major theory attempting to extend the Standard Model, from supersymmetry to extra dimensions, naturally predicts the existence of particles with properties matching dark matter. What leading physicists at institutions like Caltech, Cambridge, and the Max Planck Institute increasingly believe is that dark matter isn't a single substance, but potentially multiple types of particles forming a dark sector of physics, parallel to, but rarely interacting with our own. There might be dark photons, dark atoms, even dark chemistry occurring all around us in dimensions we cannot perceive. This is where the evidence leads, toward a universe far stranger and more complex than the one we observe. Recent breakthroughs suggest we're entering a new era of dark matter astronomy, one that might finally allow us to see the unseeable. The Vera C. Rubin Observatory, scheduled to begin full operations in 2025, will conduct the largest survey of the night sky ever undertaken, imaging the entire visible sky every few nights for a decade. Its primary mission includes mapping dark matter throughout the universe through gravitational lensing with unprecedented precision. Meanwhile, the European Space Agency's Euclid mission, launched in 2023, is creating the most detailed three-dimensional map of dark matter ever attempted, observing billions of galaxies to trace dark matter's distribution across 10 billion years of cosmic history. But perhaps the most exciting developments are happening in the detection of dark matter's subtle effects on ordinary matter. Scientists at the Ice Cube Neutrino Observatory in Antarctica are searching for the products of dark matter annihilation, the theoretical process where dark matter particles collide and destroy each other, producing neutrinos and other detectable particles. If WIMPs exist, they should occasionally meet and annihilate, creating showers of particles that ice cubes detectors, buried a kilometer beneath Antarctic ice, might observe. Other researchers are examining whether dark matter might interact with atomic nuclei, not through collisions, but through extremely rare quantum processes, creating signals so subtle they require years of data to detect. The upcoming Lux-Zeppelin experiment in South Dakota will be 50 times more sensitive than current detectors, capable of detecting dark matter interactions that occur less than once per year in its entire 10-ton detector. What this means for us extends beyond academic curiosity. Dark matter shapes the cosmic environment that allowed life to emerge. Without it, galaxies would never have formed at the right times and in the right configurations to produce the heavy elements necessary for planets and biology. The ratio of dark matter to ordinary matter, that precise 5-to-1 ratio, appears to be critical. Computer simulations suggest that if dark matter made up significantly more or less of the universe's mass, structure formation would be fundamentally different. Too much dark matter, and galaxies would form too quickly, creating massive black holes that prevent star formation. Too little, and galaxies would never form dense enough to trigger efficient star formation. We exist in what appears to be a precisely balanced universe, and dark matter is one of the weights on the cosmic scales. Here's what keeps physicists awake at night. What if dark matter isn't just passively sitting there, holding galaxies together? What if it's dynamic, evolving, interacting with itself in ways we haven't detected? Recent theoretical work suggests dark matter might form structures on scales far smaller than galaxies, dense clumps, streams, and possibly even dark matter planets or stars, objects held together by dark forces we know nothing about. These structures would be completely invisible, detectable only through their gravitational effects. In 2021, astronomers reported unusual gravitational lensing patterns that couldn't be explained by any known distribution of visible or ordinary dark matter. The patterns suggested the presence of compact, dense structures with masses similar to small asteroids, but made of something that emits no light. What are they? Dark matter clumps, primordial black holes, or something we haven't even theorized yet? The most profound implications emerge when